Basics of functions and their graphs preparation. These are some parent functions or basic functions. You should memorize most of these one way or the other. I do show you a chart for each of these to show you how you kind of come up with it yourself. All right, so the basic one with some numbers in here. So you have the linear first power one, right? This is the first power, and you can see that it just goes straight up. It has a goes a 45-degree angle. Over here you see a second power. So it's a quadratic. This is what a quadratic looks like, a basic one. Now notice that the first two actually have, well, the very first one has infinite domain. Domain are all the x values, right? So that's the domain. Domain have to do with x values, and range has to do with all the possible y values. So the domain on this one is all x values. So you can plug into the right. There's no limitation. You can plug in any x value, and then of course that will spit out any kind of y value. And you can just kind of think of f of x as y at this point. That's not a bad idea, right? So again, f of x is really kind of y. Okay, the second one, you see it hits the origin, then goes up. So all the x values, this one just keeps going off to the left. It also keeps going off to the right. So we would say the domain on this one is negative infinity to infinity. It goes all the way to the left forever, goes to the right forever, and there are no holes in it. So it has a negative to positive domain right here. That's what this is right here. It's the domain, right? Again, x value. Now, as far as the y values go, the smallest value is right here at the origin, right? And then it goes up from there. So this one includes 0, which is why we have to include this bracket, right? But then it just keeps going up forever, which means we go to positive infinity. Okay, so let's go to the next power. Now, this one is a third power. It's a third power one, right? Now, notice that this keeps going to the left forever, and this over and over goes to the right forever. It doesn't go very quickly, but it does keep going to the left and right forever. Therefore, the domain, again, is negative infinity to infinity. But the range on this one, this is a little different. It goes down forever. It goes up forever, right? And there's no holes in it. So this also has a range. The possible y values are negative infinity to infinity, which is written like this. Now let's do for the square root. Okay, square root, it looks like if we do the domains, it starts at the origin, which means we have to include 0 for the domain right here. But then it goes off to the right forever, which was where we get the positive infinity. Okay, and that's the x value. The y value, again, is up and down. So it starts at 0, the same origin. It starts right there. So that, again, we have to use bracket because it includes the 0. And then it goes up forever, up forever. It goes up slower, but it does go up forever. So we have a positive infinity there. The next one is an absolute value. This is kind of an interesting one. And again, you see whether you plug in a negative or positive, you get the same y value. In that way, it's actually quite similar to the parabola than if you plug in a negative or positive, whether it be a negative 2 or positive 2, you get a 4. Whether it be a negative 1 or positive 1, you get a 1 that it spits out. So in that way, it's similar to the quadratic. Okay, so we plug it in there. Plug in 0, absolute value of 0 is 0, absolute value of positive or negative 1 is 1, absolute value of positive or negative 2 is 2, absolute value of negative or positive 3 is a 3. So that's how you get the ordered pairs to plot and then graph this. Now at this point, it looks like it goes off to the left forever, it goes off to the right forever, there are no holes, so it looks like we have, again, a domain of, and again, domain's all the possible x values. It has everything. Now, in this case, though, it starts at 0, and then it goes up on both of these sides, doesn't matter, but on both sides, it goes up forever, so we do have to include 0. It starts at 0, but then it goes up to infinity, goes on forever. Now, you might think there's a whole lot more of these to memorize, and you might be right, but I do want to point out that with a few tweaks, these can represent quite a few different ones. We could put a coefficient in front of the first power one right here. We could put 2x plus 1. We'll learn how to graph those later. But I do want to point out that there's very similar graphs with even exponents here. All that would happen is as you go up in the exponent here, is that the graph would get skinnier, right? So instead of being there, the next one's going to be a little bit skinnier, right? It's going to be like that. It's going to be a little skinnier looking, right? And then as this power increases here, the graphs will just keep getting skinnier and skinnier with each increase in an even power. So if you know what a parabola looks like generally, you actually do have some idea of what all even power exponents look like. They're going to look just like the parabola, but skinnier and skinnier. They're going to be stretched out more and more. Now, the same kind of concept applies to this one over here, right? So again, you might think, oh, I just learned the third power one, right? I have a third power there. Okay, you'd be kind of correct, but the thing here is, if you increase the power, right, to some odd, right, some odd power, you say, you know, f of x, or let's just say y is equal to one of those, then what would happen is you'd end up with the same one. You'd end up with the same looking graph, but it would just get skinnier. So instead of this one, the fifth power might look something like this. It might look really, really skinny, and then like that, and then like that, right? Oh dear. Ah. So it gets skinnier and skinnier, right? So if you know what the cube looks like, you actually have some idea of what a fifth level or a seventh level or even ninth level looks like. It's just going to keep getting skinnier and skinnier. So it'd be just like the original one, but it would be even skinnier. Okay, same thing's true on this one. This is actually a square root, but there are other ones like there's a fourth root. That's a 4, believe it or not, fourth root. Or maybe you could have a sixth root, or you could have an eighth root. You get the point. Same kind of thing, but it's going to be skinnier, right? So it's gonna look more like this. It's gonna be a flatter looking one, a skinnier looking one, a flatter looking one, right? Okay. So I just wanted to point out that it's a good idea to memorize, to be very familiar with these, but realize that you're not just memorizing these base ones. You're going to be able to generalize it to higher powers, or, you know, on the first one, it may not be higher powers, but different coefficients. It's going to look more steeper. We're going to get to that. Parabolas are just going to get skinnier at the fourth and sixth power. Even powers going to look like parabolas, but skinnier. Higher odd exponents are just going to look just like this cube one, but they're going to get skinnier and skinnier as it goes on. Even the roots, same kind of concept. Even roots are going to look just like this. They're just going to keep getting flatter and flatter as the roots increase. They'll just get flatter and flatter. Absolute value is kind of a different one. We will be dealing with odd roots later on, but I don't have an example on this.